Hello guys, we are now on chapter 7. So this lecture is intended to present the concept on beam columns. So beam columns are defined as members which are subjected to some degree of bending and compression. Okay, so it's an actual flexural member. Uh, so this is the flexural part, the beam part, and this is the compression part, or the actual compression. So in preparation for our frame analysis, we need to learn how to deal with such members. And note that in this figure shown, okay, in this figure shown, the members AB, CD, AC, CE, BD, and DE, practically all the members except for this dotted member here, which is member CF and ED, are regarded as a beam column. So this brace here happens to act differently. Maybe a tension or a compression member which behaves differently from the beam column behavior that we are about to discuss. So the interaction formulas, when you say interaction, we are now dealing with the beam plus the column behavior. We will try to examine first the individual resistance versus load criteria of the beam column element. So we recall that the resistance must always be greater or equal to the load. Therefore, if we want to make a comparison of safety, okay, requirement, we can restate this criteria into a unity equation. Okay, so this is a unity equation wherein the load over the resistance, which is a factor, must always be less than or equal to 1 to assure that your criteria falls into safety provisions. So for compression member columns wherein your load is represented by PU and your resistance is represented by VCPN in LRFT, equation is in this form, while in AST, the load is represented by the P allowable and the resistance is represented by Pn over omega c must be less than or equal to 1. For flexural members, all we need to do is to change the variable of concern from P to M, and the same result for LRFD and ASD. Same form will result to the safety criteria. So for a beam column in which both bending and axial compression now interacts, which means to say that we simply superimpose the effect of the two limit states on bending and compression. So the LRFD and ASD may be shown in this form. Okay, so this is now considered an interaction equation for a beam column in LRFD and ASD. So we simply sum up the effect of the axial compression and the flexural or bending to represent your safety criteria, known also as the interaction equation in LRFD and ASD. When biaxial bending is then considered, the only difference is we will be having two moments. No? Still, the superposition of the axial compression plus bending in two directions will follow the unity equation we have described above. So this is again both in LRFD and ASD. Of course, the subscript X and Y refers to the bending about the X and Y axis. For the AISC interaction equations, all we need to take note are the added conditions into which your safety consideration will be properly provided for in the code. So for large axial loads, which means that your member is acting more like a column than a beam, this is now a column dominant condition, you will notice that the equation above in LRFD was given a reduction on the moment. Okay, so this 8/9 is a reduction on the applied moment. Okay, since the applied moment is an ultimate moment, it is a factored moment, then this is MUX and MUY. So for the large axial load case, our criteria for consideration is the ratio of your axial load all over the capacity, or the load over the resistance ratio in LRFD must be greater or equal to 20%. For small axial loads, this means that this is a beam behavior dominant, okay, or a flexural dominant condition wherein P over VCPN, your actual load ratio is less than or equal to 20%, then we consider a reduction on the applied actual load. Or the applied actual compression. So take note, this is this 1/2, 50% reduction, and 8 over 9, almost 90% reduction in the applied forces. For ASD, the reductions are just the same, and the condition upon which your behavior is being evaluated is the same. The only difference, of course, is how the applied forces, okay, here the applied forces are in terms of service moments, okay, and your applied, okay, actual load is also a service load. Okay, so the same form of the LFD equation is shown here for your ASD. So let's move on to the analysis method, the basis for which we will be considering our analysis for columns and for beams behaving as a beam column. So we consider a beam column with an actual load and transverse uniform load. Then, in this particular figure here, we notice that the failure for a beam column subjected with both a transverse load and an actual load. Okay, so here the transverse load will trigger the behavior on bending, while the actual load will, of course, aside from having the actual compression, the stresses present on the member will actually contribute also to the buckling or the bending failure in this case. So if we consider an arbitrary point O into which this free body diagram has been based on, we can make use of equilibrium conditions in order to solve for this moment at point O. But notice that there will be an additional moment that will be added to the moment induced by the transverse load because of this deflection y at point O. So this deflection y is a maximum at the midspan if you are considering this type of beam. Okay, so delta, where delta now is actually the y maximum, or more or less at the midspan for this beam. Hence, the total moment now will be a combination of the transverse load moment, which is simply a uniform load moment for a simply supported beam, plus a P delta. So if we are looking into the maximum moment, it will simply be equivalent to WL squared over 8 plus P times delta, okay, which is this one here, noted no, in this explanation. So take note that for ordinary structural analysis method, which do not take into account the deformed geometry, these are called first order analysis or methods. So when the deformed geometry coming from the initial conditions on the frame is not accounted for, okay, it's not accounted for, then we call that the first order methods. But the reality is such that your geometry will somehow be deformed and cause some additional forces, especially moments. Then we have to consider an extension of your first order analysis, which is called a second order analysis, normally done by simple iteration procedures. In addition to secondary moments caused by the member deformation P delta, so this is P delta, small delta, additional secondary moments, which is the P big delta there, the Greek letter delta, are present when one member translates with respect to the other. So this is now the difference between a P delta scenario and a P delta big delta scenario. Okay, so P small delta scenario and a P big delta scenario. So you notice that here your member has no translation, while here your member has a lateral translation. Okay, so this is without translation or no translation, and this is with lateral translation. Okay, specifically we are referring to these two members as a column member, which will behave as a beam column. Okay, so this real column will behave as a beam column. So the translation is given here in terms of your big delta, while here there is no end, okay, displacement or translation. There is a deflection, okay, you can use the term as a mid-span deflection for your column member. Hence, the distribution of moments in the member is a combination of the primary moment P delta and P delta moments, or P small delta and P big delta moments. So this behavior is very much true for an unbraced frame, or what is known as the moment frame. Okay, so in frame analysis, this refers to a brace frame. or a brace column. And this is an embrace column or an brace frame. Okay, so here your distribution of moment for this particular is a combination of your P delta plus P delta, okay, for your moment. So the delta here is of course the small delta here represents, okay, the primary, sorry, not the primary, but rather the displacement or deflection brought about by a transverse load, in case there is any. Okay, let's move over to the AISC guideline for the methods that you can consider for stability in the design of a beam column. So this is referred to the AISC specification, chapter C, wherein three methods were actually defined. The first one is the direct analysis method, okay, where the effective length K, factor K is assumed to be all equal to 1, but the member stiffnesses are reduced. Okay, so there is what you call a stiffness degradation in this regard. Wherein the material non-linearity, okay, non-linearity is considered. So this is material non-linearity. Okay, for the second method, the effective length method, K is determined based on stiffness of the member. K is determined based on the stiffness of the member, or K is determined based on stiffness rather, and the member stiffnesses are not reduced. So which means to say that this is K a function of some of your EI value. Okay, so this is the flexural rigidity let's use the word K proportional to EI, while your stiffness, no reduced stiffness. Let's not use K as your stiffness, no reduced EI in this case. So for the first order analysis method, which is the easiest and the most popular method you can see from the book, the effective length K factor is normally used equivalent to 1, just like your direct analysis method. The member stiffnesses are reduced. So there is material or there is stiffness degradation here. Okay, so these are normally based on code uh, provisions. So if you are using an AISC, you may refer to the AISC code. Okay, this is more popular. These two methods here are more popular for softwares because they consider your second order analysis. So this is a second order iterative analysis. Okay, while here you are only using a first order and last method, and this resembles the method you can see as the moment magnification or moment magnification uh, method, or sometimes moment amplification method. So magnification and amplification may be used interchangeably. Okay, so that's it for the first lecture. We will proceed with the concepts on moment amplification method on the next video. So thank you for listening.